Okay, welcome everyone to another installment of Final Talks for Astronomical Techniques and Instrumentation. Today's talk is being given by Seelig of the Rochester Institute of Technology, and he'll be talking about data reduction of an active galaxy.
Good afternoon, my name is Seelig. Today I'll be discussing the data reduction I performed on the active galaxy NGC 4180. So, the reason for this project is to search for mechanisms of gas transfer in NGC 4180. This is part of a larger project trying to understand how these mechanisms affect the evolution of the surrounding galaxy. As you have large amounts of energy being emitted from the central region, as well as gas flowing into the central region. So today I'll be discussing the accretion disk, the torus, the broad and narrow land region, and then I'll discuss the GMOS North, the Gemini North GMOS IFU, the spectroscopic standard star I reduced, along with NGC 4180, and then I will talk about analysis that I intend to perform in the future. So, in their 1995 paper, Uri and Padovani included this figure, which is descriptive of what many believe to be a model of AGN that unifies all the classifications of active galaxies that exist, in which you can see that, in which using this model, you can determine that all the classifications are orientation dependent, in which the viewer's orientation to the active galaxy determines what type of AGN you are looking at. So this model shows the obscuring torus, the black hole, the accretion disk, the broad line region, the narrow line region, and the jet. What it doesn't have labeled is that there should be a corona, a hot corona in the central region there around the black hole area. So of the many different classifications of AGN, there is one type which is a safer galaxy, which is a safer AGN. There's two different safer types. There's safer 1 and safer 2, and then there's a I believe there's a whole slew of tertiary safer type galaxies. So what makes a safer 1 galaxy a safer 1 galaxy is the broadened permitted lines with respect to the forbidden lines. So in this diagram, in this spectral diagram, you can see that the H alpha line is much broader than the N2 lines and overtakes them. But in this, if I show you this one, you can see that the H alpha line is narrower than the N2 lines. This is one classification of AGN, and the reason I'm including this is because NGC 4180 is a safer type galaxy. So the accretion disk that was shown in that model, the accretion disk, from the accretion disk, gas falls onto the supermassive black hole, which releases the large amount of gravitational energy. So from this, from the bolometric luminosity, if you measure the bolometric luminosity using this relation here, you can determine the accretion rate of the mass onto the black hole. In their text, in their text, astrophysics of planetary nebula and active galactic nuclei, Osterbrock and Furlan have demonstrated that if you assume a 10% accretion efficiency and volumetric luminosity of 10 to 12 solar luminosity, you can have 0.7 solar masses being accreted per year. Other papers that I've seen have, using a similar accretion efficiency, have suggested that this number can be as small as 10 to the minus fourth solar masses. I believe it's fairly, I believe 10% accretion efficiency is fairly typical accretion efficiency to assume, which, I didn't mention it, but eta in this case is the accretion efficiency. M prime is the accretion rate, and c squared is the speed of light. So the other part of the model was the torus, which the torus is a donut-shaped ring which surrounds the central region and can extend possibly from 10 parsecs to a couple hundred parsecs. But as of now, I believe the torus has not been directly observed because we don't have, I believe we don't have the resolving power to observe it in the nearest AGN. So knowing that, then Mason, Rachel Mason suggested in one of her papers that this region should be smaller than 3 arc seconds. So the torus will absorb radiation from the central region and re-emit it in infrared at approximately 1 micrometers, creating a bump in the spectral emission diagram. The broad and the narrow line region. So the broad line region has a typical cloud density of 10 to the 9th electrons, and the narrow line region is 10 to the 5th electrons. Depending on whether your orientation to the central region and where the torus is determines whether or not you can see the broad line region. So so the broad line region. So whether or not you can see the broad line region determines whether it's a safer 1 or a safer 2 AGN. The broad line region is closer to the black hole, and it has a larger velocity dispersion, which will create which will cause the emission lines to be broadened as well. So the data that I had was acquired from the Gemini North facility in Mauna Kea. This is one of 2 facilities, two Gemini facilities. One is in Mauna Kea, Hawaii, and one is in Chile. Both of them have 8.1 primary mirrors, and both of them have a GMOS IFU unit, Gemini Multi-Object Spectrograph Integral Field Unit. The integral field unit, this is a diagram of the integral field unit in which there are 2 mirrors here, one for a red slit and one for a blue slit. And after the light is collected by the primary mirror, it gets directed down onto those mirrors and then redirected into these optic fibers here, which then get directly onto slits. Which get directly redirected onto slits to create the spectrum. This ends up creating a data cube, which is a two-dimensional, which is a cube of data which can be thought of as a stack of images, with each image being a different spectrum. So then at each what is regularly a pixel, that would be actually a spaxel, which is a three-dimensional pixel for each part of the data cube. So you have two dimensions that are spatial and one dimension that is spectral. A little bit about the Gemini North IFU is my data was collected with the red slit. I showed you that there was two slits, two parts. One was a blue slit, one was a red slit. Mine was collected with the red slit. Has a 5 arcsecond by 3.5 arcsecond field of view. If you were to combine both slits, you'd have a 5 arcsecond by 7 arcsecond field of view. But because you'd have combined them both, you would have a decreased wavelength range. So if you only use one of the slits, in our case the red slit, you would have a smaller field of view, but a larger wavelength range. So you have about 500 lenses per slit, and each lens slit has 0.2 arcsecond field of view. I believe you can't use, for the Gemini North unit, I believe you can't use the blue slit because there are too many broken fibers. And fibers are very important because that's where the light comes from. So I'll show you later on with my data, one reason why knowing where the fibers are is important. So this is the spectroscopic standard star that I used in reducing my data. The purpose of it was for flux calibration of the galaxy data, in which you can see the stars at the center there. And this is, I believe, a fairly typical spectroscopic standard. Looking through several papers, I noticed it being mentioned a lot. And the purpose of this, so I produced the data of the spectroscopic standard star first using IRAF. The Gemini facilities recommend using their packages that they have in IRAF to do the data reduction. And using that and a cookbook that was put together by Dr. Lena, I began producing the spectroscopic standard star first. And the purpose of doing the spectroscopic standard star first was to familiarize myself with the data reduction process, but also to make sure that there wasn't any, to make sure that I had all the kinks out of the process first. One of the interesting parts of this was that the Gemini North and South telescopes don't have an atmospheric dispersion corrector, an ADC. And so what ends up happening is when you have your data, it becomes blurred along different wavelengths. It becomes kind of, so you'd have kind of an image like this, and if you looked at it at each wavelength, it would kind of shift across the frame of the image. And the reason for that is, if you look at the spectrum, you'll notice that the spectrum will either rise or decrease with the image. So, knowing that the image is not the third dimension isn't time, but the third dimension is spectral, you know that the entire spectrum of this object is spread out across the frame. So the way to correct for that is actually rather simple, and for Fortunately, the Gemini team has provided an algorithm that is basically just turn on a feature at the last step of the data reduction. And knowing the temperature and certain qualities, I believe, of the viewing site, they're able to eliminate the curve that you see in the data and thus kind of contain your image to one point where it should actually be. And this is what I ended up getting. So this is a 5 arcsecond by 3.5 arcsecond field of view at 600 nanometers, and this is the final product of the standard star, which is a fairly nice point source. So this is a Sloan Digital Sky survey of NGC 4180. It's 3.2 arc minute by 3.2 arc minute, and it covers what is pretty much the entire visible galaxy. So that's 3.2 arc minutes by 3.2 arc minutes, and the data that I have is focused on 5 arc seconds by 3.5 arc seconds. Actually, it's focused on two frames because the telescope was offset during the exposures, so it took an image at one point, it took an image at another point. So it's actually a 5 arc second by 7 arc second image. But this is where I ended up kind of reaching a point in the data reduction where I need a little more time, is during the offset phase. So there's two parts about this data cube right here, which is shown. This is the central parsec, the central kiloparsec of the galaxy. But as you can notice, there is a black bar at the top of the image, and the image is kind of cut in half. Well, the black bar at the top of the image is, I believe, caused by what I mentioned earlier was the fibers. When I talked earlier about the fibers that are used to direct the light from the image plane down to these slits. Well, the fibers, if you do not identify them correctly, their positions, if you do not identify them correctly during the interactive part of the IRAF data reduction, you end up getting the individual pixels shifted around and causing what I believe is a feature like that. So I'll have to look back into the data reduction process to determine whether I've identified the fibers correctly. The other part of this is that I have 3 other data cubes, one other similar to this, and 2 others that should actually mirror to the other side, showing the other half of this central region. The 3 other images, one of the images I said was similar to this one. It's actually at 555 nanometers. The wavelength, the central wavelength is at 555 nanometers, and the other 2 images are similar in which one is 550 and one is 555. The purpose of one of them being at 550 and one being at 555 is there's a 5 nanometer wavelength dithering to cover the CCD gap in the spectrum. But using this image as a representation of the central kiloparsec region, at the pixel 3330, which is about somewhere in here. Looking at that pixel, you can see the spectrum of the image. Now, I apologize for the axes; they're not labeled, but the bottom axis is wavelength, and should be, and the Y-axis, I'm not actually sure yet what that is because I haven't had a chance to look at it and figure out what the y-axis is correlated with. But at this pixel, you can see several features which are typical of an AGN. So in the spectra I showed you earlier, there was the H alpha line, the nitrogen 2 lines. There was an oxygen 1 line, and I believe there's also some sulfur 2 lines. And the sulfur 2 lines are here in the image. There's one here at about 6716 angstroms and 6730 angstroms. And then there is the H alpha line, which is in between the two nitrogen 2 lines. I mentioned that there's an oxygen 1 line, which I believe is this small little bump here. In other pixels, that oxygen 1 line becomes stronger. Another thing I believe that this line right here is where one of the chip gaps is. So this is an undithered image, and so this shows where one of the chip gaps is, and I believe right here is another one of them. So the dithering should offset the image enough to eliminate that flat line. So moving forward, we'll be performing analysis on the entire data queue once it has been combined. And from this, I will attempt to assemble different maps of the galaxy. One of them being a velocity map, one would be a velocity distribution map, and one would be an electron density map. The electron density you can obtain from the S2 line ratio, so you take one line, the intensity of one line, and you take the ratio of that with respect to another line. The velocity of the gas can be determined from the Doppler shift, so the central peak of the lines, with what has been observed in a laboratory setting. And the velocity distribution of the gas can be determined by the line broadening. You can also, from the data queue, from the spectrum, you can also determine at different points of the data queue whether or not the gas is moving towards you or away from you, showing a velocity gradient by whether or not the spectral lines have wings, in which you have a more in which you would have a spectral line which would kind of have a broader side than the other side. And that would show you whether or not the line has been shifted. So my project will, going forward, like I said, I will complete the data reduction. I will use Gaussian curves to model the spectra, and then I will assemble the maps, the velocity maps, the velocity distribution map, the electron density map, and that will hopefully encompass it. Any questions?
Okay, great. We have time for questions. Anyone? Chief?
What is your science question, Seelig?
Oh, so the purpose of this research is to search for the mechanisms of the gas transfer of NGC 4180. So what is not known right now about, what is poorly known about AGN is how how the transfer of gas, the different transfer mechanisms of gas from the kiloparsec region to the central parsec region affects the evolution of the galaxy itself and what impact it might have on the surrounding area. Another thing that needs to be better understood is what the mechanisms of transfer are. There are extrinsic causes and intrinsic causes of inflows and outflows of gas to this region, and so those need to be studied a little bit better to understand.
So if you were to try to pick just one question, it could be, what's the mechanism for mass inflow? Is it into the central region? Is that a potential question?
That would be one question.
Okay. And if you want to choose that question, have you constructed a project that would answer that question? Is it the case that when you finish this, you'll publish this, let's say, and then you will have solved the mass inflow problem for AGN, and then you'll go to Stockholm and get a Nobel Prize? or is it like you'll learn just a little bit, or how does that work?
I believe that I would have learned a little bit regarding the matter, and that could be piled onto the compendium of knowledge about this, which would increase the understanding of how this occurs. This is actually part of a larger project, ongoing project right now, in which Dr. Lena studied several AGN, several nearby AGN. So this is a continuation of that research.
And is there anything special about 4180?
4180. Not that I know of. Seems not that I know of, actually.
Why did you pick it?
I actually didn't pick it. The data was given to me as part of a data set that was obtained from time grant on the Gemini telescopes.
How many galaxies were covered in that project? Or do you know?
I don't know off the top of my head, but it's there. Let me think. There was multiple multiple observing times allotted. I can think of two. I don't know if there's more than two, but I believe there's 2 times allotted over 2 different years, and I think that there was. I couldn't give a number on how many targets were selected, but it was more than I believe it was more than 10 galaxies.
So is 4180 is a known AGN, right?
Yes.
Okay. And did you read any papers about 4180?
I did. I looked into it. There doesn't seem to be too many papers specifically about 4180, or what could be also 4180, which is 4182, which is another, which was something that was suggested by a group who had done, I can't remember which survey, but they'd done a survey and suggested that they included 4182 as a different galaxy, but it could also be 4180.
I only found one paper with 4180 in the title, and the title was a big, long telephone book object, and then in parentheses at the end it said not 4180.
Yes.
So I ended up not learning about 4180. Are there any other questions? There must be a lot of questions, no? See if I have any more. No, I think that's it. Okay, let's then Trent again.